Hi guys. Um, I decided what I think today is going to be. There's not a quiz, but also as I was preparing these examples, um, I decided I just wanted to kind of work through some examples that I prepared, um, just so we can see what some of the different problems are like, and um, because they're kind of long and I want to make sure that we really have the time to talk about them. So we won't be breaking up into some smaller rooms, but we'll just be um, going over some extra examples. What I also wanted to say is, as we're talking about these series, so this is a version of what would show up if we were taking an in-class exam. Um, but what I want to point out is that some of these series we're going to see tomorrow. But basically, there are some series which you do not have to justify where they come from. So today, in one of the examples, we're going to be doing something with arctangent of x. And in class yesterday, we worked through where this series representation actually comes from, and we actually checked that it has a radius 1 and it converges at the endpoints too. So in any problem going forward, if at some point it would be helpful to know a series for arctangent, we can just go ahead and use it. And similarly, once we introduce, kind of see where they come from, the series for e to the x sine and cosine, you don't have to justify those. Those are just kind of black boxes. We'll say these are known series. If you need them, use them. Okay. Right. And I think this formula sheet, it's all stuff that, I mean, it's a take-home exam for the final, so you have access to it, but I'm going to include this on the exam just because it might be nice to have it all in one place. So this has a lot of the things from different parts of the course: trig identities, basic integrals, some new power series stuff, a unit circle. So this sheet is going to be on the final exam, not because you can't look it up elsewhere, but it's kind of nice to just have. And today I'll be referencing these two series. And I'll just use them without mentioning where they come from. Okay, so actually, hold on a second. I uploaded these, but I didn't combine them into one document. Sorry. So now we're good. So let's talk about some of these problems involving power series. So the two big types, especially so far, are you're given a series, a power series. So it has some variable in it, and it's always going to be some variable raised to a power. There's other stuff around, like a factorial here, and n 2 to the n, but it's always going to be x plus something or x minus something raised to the n is where the variable shows up. And so a question, if you're given a power series, is figure out when it converges. So some quantities that we can ask are find the center, which is really just reading it off from the form of the series, and then find the radius of convergence and the integral of convergence. And to do that, we'll need to use some of our convergence tests. The other type of question is you're given a function and you want to find a series for it. And this is where using some of those known series are useful. So in this second case, the second problem here, what we're going to do is we're going to use this series right here. It's not exactly the same, but it's a fraction with some x's, so we can try to turn this into a function that has this form a little more explicitly. And also we have the function x times inverse tangent and then the derivative of that. So what we'll be able to use is we know the formula for the series for arctangent, manipulate that series in order to get series for what happens if we multiply by x, and then what happens if we take the derivative of that. Okay. So we'll come back to these when we need to, but let's talk about these first two. So when we're trying to find where these converge, the tests to really think about are the geometric series test, the ratio test, or the root test. Those are useful because they end up saying, depending on, or you get convergence if some quantity is less than 1. And that's what sets up an inequality for deciding which x actually make this converge. So in the first case, if we want to decide when this converges, if we're looking at this, the n factorial, that says you want to use the root, sorry, you don't want to use the root test, you want the ratio test. Really, with any factorial, the ratio test is the series test which is best suited to decide if it converges or diverges. So if we apply the ratio test to this series, then the ratio test says take the limit of the absolute value of an plus 1 over an, which means take the absolute value and put the terms of our series on the bottom. So there should be an n here, it's missing. And then take the terms of your series and put n plus 1s in there and put those on the top. When you have a power series and you have x's in here, what happens is that absolute values, you're able to break that up over division and multiplication. So we can take the absolute value and really bring it just on x minus 1, and then raise that to the power. So the exponent n plus 1 is now outside the absolute value. And the n, which is supposed to be here, is also outside the absolute value. And n plus 1 factorial and n factorial are positive, so absolute values don't do anything to those anyway. So we put the absolute values on our x minus 1s, and like the ratio test usually goes, take the bottom, flip it, and multiply that instead. And then, like happens whether it's a power series problem or not, we do some cancellation. The absolute value of x minus 1, these two terms, we get some cancellation because there are n factors in the bottom, n plus 1 on the top. If you subtract those exponents, you just get one single absolute value of x minus 1 on the top. For these n factorials here, n factorial is 1 times 2 times so on up to n. N plus 1 factorial has all of that, but then an extra factor of n plus 1. So if you write the factorials out as multiplication, everything cancels except for this extra factor of n plus 1 on the bottom. So after canceling, now we take the limit. In this case, what can happen, and the next example we really see this, is this limit can possibly depend on x, because it might matter for different x's, this series converges or diverges, and so this limit will kind of reflect the way that convergence depends on which x you pick. In this case, because n is the variable that's changing, the top is just fixed, x minus 1. The bottom, n plus 1, is growing. And when we have a constant divided by something going to infinity, that limit is 0, no matter which x you pick. So while x is being thought of as a variable, the way we're doing this is that pick any x at all and see what happens. And this work would show you that no matter which x you started with, the limit is 0. So that means that for every x, this limit is 0. And since for every x, the ratio test says converge, that means that our series actually converges everywhere. So to answer the questions, to give the quantities that we're looking for, the center, we could have done that at the very beginning. That is where you look for the power of x, or where x shows up, and it's x minus a, that number being subtracted, that is what the center is. So because it's x minus 1, that's our center. And you can always just read off the center from whatever the power series formula is. For the second two, we don't really have to do any more work, because once we find out that no matter which x you pick, you get 0, that means no matter which x you pick, the series converges. And when that happens, the radius is infinite, and the interval of convergence is everything. So if you find out the ratio test always says converges, or the root test, or whichever test you're using, then the interval of convergence is everything, and the radius is infinite. Questions about this problem? So the second one is the same type of question, but we're going to have some different things going on. Right, so that's the whole thing. So here we're given a power series, again asking for the center, the radius, and the interval. So first off, the center in this case, we can focus on the power of x, because it's plus 3, and the center is whatever you are subtracting. So in this case, the center is minus 3. To figure out where this converges, in this case, as in the case before, it's not geometric. Because there's this kind of stray n here, it's not just geometric, and so we have to use the ratio or root test. In this case, you could use either one. In the first case, there's that factorial, and factorials really need the ratio test. In this case, you could go either way. I used the root test just to show you something different. But if you use the ratio test, you'll end up at the same inequality at the end. So the root test says, take the absolute value, and then take the nth root, and take the limit of that as n goes to infinity. So again, the absolute value, what it does, if there was any alternating part, it would kill that off. But what always happens with a power series is that you take the absolute value of the x plus or minus something and raise that to the power. the n, the 2 to the n plus 1 are positive, so those don't do anything. What also is helpful is that the bottom is 2n plus 1, and what we really like to see when we do these problems is we want things raised to the nth power. So we know that we can use the root to cancel that exponent exactly. So we can rewrite this a little bit, where instead of 2 to the n plus 1, we have 2 to the n times an extra factor of 2. The exponent rule lets us break it apart into multiplication. And now when we take the nth root of this, we can see that we get a lot of nice simplifying. The nth powers on this absolute value of x plus 3 and the nth power on this 2, those cancel, giving us this expression, which doesn't have any n's in it at all. So we just get the absolute value of x plus 3. The other part of the fraction, the n over 2, we don't get any cancellation, so we still have the nth root. But the fact that we can use is the nth root of any polynomial goes to 1 as n goes to infinity. So this part doesn't have any n, so we're stuck with it. This nth root of a polynomial, that's going to go to 1, which says why, when we take this limit, that part's gone. We just have the absolute value of x plus 3 over 2. So then, like happened in the ratio test example, what you do with this thing is you ask, which x's make this less than 1? And those are the ones which make your power series converge. So that sets up our inequality. If we multiply both sides by 2, we get the absolute value of x plus 3 is less than 2. And this here is where we get the radius. At some point, you're going to get the absolute value of x plus or minus something less than 2 or less than a number. That is where the radius comes from. Whenever you get to this point in the inequality, that tells you the radius. And it does need to be just an x here. So if we had something like the absolute value of 2x minus 1 or something is less than 1, this doesn't give you r equals 1. What you have to do is say, factor a 2 out of everything. So you need to divide by 2 to get to this stage, absolute value of x plus or minus something. So r equals a half. So if there's some extra factor in front of your x, you need to get rid of that. You can have something added or subtracted, and that's changing what the center of your interval is, but we don't want an extra factor there. So this 2 is where the radius comes from. For the interval, we actually solve this inequality. So that means that the quantity in the absolute values is less than 2 and greater than negative 2. And then with this string of inequalities, subtract 3, which says x is between -5 and -1. And that's most of the interval. But what you also need to check is, do we include the endpoints or not? So we know our interval is going to look like -5 to -1, but you don't know, do you have round brackets, do you have square brackets, because you don't know if you include those or not. So we actually have to take these two specific numbers, put them into this series, and then really check what happens. And as a, I guess, word of warning or caution, when you use these endpoints, you can't use the ratio or root test because these are exactly the numbers which make this limit equal to 1, which is the case where the ratio and root tests don't apply. So you're going to have to do something else, some comparison, alternating series, just something other than the test that you used the first time. If we put -5 in, so this is our power series where we input -5. -5 plus 3 is -2. We can break things apart a little bit. The -1 raised to the nth power and 2 raised to the nth power. That gives us some cancellation, so we're left with -1 to the n times n over 2. And this series diverges because if you take the limit of the sequence, -1 to the n times n over 2, that diverges. Half of it goes to infinity, half goes to negative infinity. And a similar thing happens if you put in -1. There you just get 2 raised to the n. Some factors of 2 cancel, and your series becomes n over 2. And this sequence goes to infinity, so the series diverges by the test for divergence. So this means that if you actually try -5 and -1, the series diverges. So we include everything in between, but not the endpoints. And that's where this interval of convergence comes from. Questions about this problem, which has some more going on than the previous one? All right, so for this type of question, given a series, what's its interval and radius of convergence? You use the ratio or root test. If you use a geometric series test, you don't have to check the endpoints because geometric series always diverge at their endpoints. But the ratio and root test have their endpoints as what puts you in this indeterminate case, so you really have to check it. And to use that it's geometric, it really has to be only some expression involving x raised to the nth power. You would have constants, but you can't have an n like we did here. All right, so problem 2 says, here is a function. Find a series for it and find the interval of convergence, the radius and interval of convergence for that series, which is really telling you find the interval on which the series you come up with matches and gives you the same values as this function we started. How we want to do that is we want to say, take a function that we know we have a series for. And the most basic one is 1 over 1 minus x is equal to the series x to the n, as long as the x's you put into the two sides have absolute value less than 1. And what we can say is, if we can make this expression show up, 1 over 1 minus something in this function, then we can take that something and put it in for this x, and that's what's being raised to the nth power. What helps on the way is it looks like the negative's in the wrong spot. We have some x term minus 1, and we need 1 minus x. So if we multiply the top and bottom by -1, which keeps the fraction the same, then we have a negative on the top. We're flipping the sign of the bottom, and we get 1 minus 1/2 x cubed here. And that is closer to this form. What we can also do is say, the minus x squared, let's forget about that for a second. And just focus on, what if we just had a 1 on the top and the bottom is still 1 minus 1/2 x cubed? And this is the form that we were looking for. 1 over 1 minus something. Here we have 1 over 1 minus x. And so what we can say is, in this form, the x here is what was raised to the nth power. So we can use the same form, but now this something here is what's raised to the nth power. And after a little simplifying, so an exponent rule, multiplying these exponents to give us 3n, and then raising the 2 to the n in the denominator, this series, x to the 3n over 2 to the n, is the series which represents this function. As long as the thing in here is less than 1. Because we could make this move going from 1 over 1 minus x to the series x to the n, as long as the thing, the x, has absolute value less than 1. So that requirement is still here when we have a more complicated something. We can still have the same form of a series as long as that something has absolute value less than 1. So that's what sets up the inequality to see where this series represents this function. And if we work on this inequality, the first thing is we can factor out a 1/2, and we can take the absolute value of x and cube that. Then multiply both sides by 2, and then take the cube root. And so the x's that make 1/2 x cubed less than 1 are the x's that are have absolute value less than the cube root of 2. Those little x can go. So that gives us our radius. And that's going to be wrong there. So this is our radius, and this is our interval. And because we started with our geometric series and we substituted something in, the endpoints are also not going to be included. So in the basic geometric series, we don't include 1 and -1. That makes the series diverge. We also don't include the endpoints at this stage right here. And you can check kind of explicitly, if you take either of these numbers and put them in here, they give you 1 or -1, and those are values which make a geometric series diverge. So that answers the question for 1 over 1 minus 1/2 x cubed. But the real question was, what happens to this function? And what is nice is extra factors of x don't change anything. You can just multiply them through, and they distribute. They show up on every term of the series, but that just means in the formula for the terms of the series, they have 2 extra factors of x, and they have an extra minus sign. So the original function f of x, we can write it as -x squared times 1 over 1 minus 1/2 x cubed. This fraction we dealt with already. That's what this first step was. So we can represent our function as -x squared times this series that we just found. And then what we can do is multiply this negative and this x squared onto all of the terms. And if this is what each term looks like for different choices of n, then multiplying by x squared takes those exponents and gives you 2 extra factors of x. No matter how many factors of x you had to start with, we add 2, and that's our new power of x. And if this is what we're doing, sorry, that's not what it should be. When you take a series and multiply by some power of x, the radius and interval stay the same. So because our original, or this series that we found here, has radius square root of 2 and interval negative cube, has radius cube root of 2 and interval negative cube root of 2 to positive cube root of 2, if we multiply that series by x squared, we get exactly the same radius and interval of convergence. And this last line here is just, if you want, this is the actual series. So this infinite polynomial, everything's negative, the powers keep increasing by 3, the denominators keep doubling, that series is equal to this function, as long as you're in this interval. Questions about this example? Okay. So this is a fact we're just allowed to use, and we want to recognize this function we can find sort of at its core a function that looks like this, use that we know what functions like this look like as a series, and then allow for the extra pieces that there are. The extra minus x squared, the fact that it's not just x being subtracted here. Okay. So the last question says, here are 2 functions, x inverse tangent of x, and then the derivative of that thing. And find series for those and their radius and intervals of convergence. So we'll kind of work our way up to this one, but where we'll actually start is that we'll take as a given known fact that inverse tangent has a series. And this, we don't have to justify it. We did the work. It's sort of a prominent enough function that we'll just say this series works, and we know its radius, and we know its interval of convergence, and we check that it actually converges at the endpoints too. Okay. So if we want x inverse tangent of x, this is a lot like the last part of the previous problem. We know a series for inverse tangent. We have an extra factor of x, so we can just multiply that x through, which means multiply every single term by x, which means every term gets an extra factor, so the power is, instead of 2n plus 1, another x makes it 2n plus 2. And when we take a series and we just multiply it by an extra power of x, the radius and interval don't change. And if you're looking to kind of verify this, or if things seem uncertain, if you take this and kind of approach this like we did the first problem, saying, here's a series, where does it converge? If you try, maybe the ratio test works the best, this is what you'll end up with. The radius is 1. When you check the endpoints, if you put 1 or -1 in here, you can use the alternating series test and see that it converges. Okay. So then where there's more work is what happens to the derivative. Now, what you really don't want to do, and that, sorry, get rid of these weird circles. In the prompt here, I said, don't actually find the derivative of the function, meaning don't use the product rule and get, what is it? It'd be whatever the product rule says, arctangent of x plus x over x squared plus 1. So you don't want to go that route. But what we can do is say, back here, we just found a series for this function. X inverse tangent of x has the series -1 to the n, x to the 2n plus 2 divided by 2n plus 1. How we can find a series for this, or the derivative of this function, so how we can find a series for this, is to take the series for the original function, so x inverse tangent has this series, and differentiate this series. So that's like saying this function, if we want to find a series for its derivative, we take this series and we're going to find its derivative. And while this derivative of this series is a big mess of calculus symbols, what is good about this is if you want to take the derivative of a series, what you do is just the power rule on the formula. So you look at this and say the derivative is going to be another series. These parts that don't have an x those aren't changing. So we still have the -1 to the n, and we have the 2n plus 1. What we focus on is the x term here, x to the 2n plus 2. If you apply the power rule to that, then you bring the exponent down, you decrease the exponent by 1, and that gives you the new formula for the terms of the derivative series. So it is a lot of symbols, but how you're going from one to the other is just the power rule, like the first derivative rule you ever learn. That's how we take the derivative of a series. And when we do this, so this is the series for the derivative, and the radius stays the same. So the original series, the one we started with, had radius 1. If we differentiate it, the radius is still going to be 1. The problem is when you differentiate it, the endpoints might change. So now we need to explicitly check our center is 0 because it's just x. It's not x plus something or x minus something. Since it's just x, the radius is, or the center is 0. So the endpoints are 1 and -1, the same endpoints that we have here. But now we need to check they converge for the original series. Do they still converge after we differentiate the series? And that means take 1 and -1 and substitute them into this series and see what happens. So if we pick x equals 1, then putting that in here, we get 1 to the 2n plus 1. 1 to a power is just 1 the whole time. So what we're left with in the series is negative 1 to the n times 2n plus 2 divided by 2n plus 1. And now we sort of forget about this was a power series and all of that stuff, but just say, here's a series, what does it do? And how we can analyze this is saying, well, 2n plus 2 over 2n plus 1, that converges to 1. If we put on the alternating part, then that sequence is going to diverge because this part's going to 1. So if it's alternating, it's bouncing around close to 1 and negative 1. So that diverges. And then we can say, we checked and the sequence diverges. So by the test for divergence, the whole series diverges. And that's all to take care of one endpoint. If we try the other endpoint, negative 1, putting that in here, negative 1 to the 2n plus 1. The plus 1 we can move over to minus 1 to the n plus 1. Negative 1 to the 2n is negative 1 raised to an even power, and that's always 1. So that's like squaring it, raising to the 4th power. All of those are just going to be 1, so we don't have to write those. So if we put negative 1 in, we get negative 1 to the n plus 1 divided by, times that same fraction that we did in the first case. So when we're here, except that the alternating starts in a different kind of phase. Here, this is negative 1 to the n, so it starts with 1. Here, this is negative 1 to the n plus 1, so it starts with negative 1. We still write down the same thing. This part of the sequence, the fraction goes to 1. The whole alternating part diverges, and if the sequence making up the series diverges, the entire series diverges. So this means that we checked the two endpoints and they both diverged. So our interval of convergence is negative 1 to 1, not including the endpoints because we checked and those don't work. Questions about this problem? There's kind of a lot going on. Okay. So that wraps up the problems I wanted to talk about. This video and these notes are going to get posted on the Canvas page if you want to look at some of these examples. And I think these are the kinds of things that you should be ready to do involving series. Either given a series, find when it converges, both the radius and the interval. And then also given a function, find a series for it. Which through yesterday is take a function you know a series for and kind of manipulate that function so we can get the f of x we're looking for and manipulate the series in the same way. Okay. So if you guys have any questions, I can stick around. But if not, there's no quiz after this. Take a look at these questions if you have any, if you need to think about them anymore, and let me know what questions you have. But if no one has any questions, I'll close things out and